Hi everyone, I hope you are all well. As you can see, we're going to be having a look at our very own planet today, the planet Earth. And here it is, photographed from the Hubble telescope, which is out in space, sending pictures back to us. And I got this off the NASA website. Now I like this picture particularly because I think it looks really beautiful with the kind of galaxy stars in the background, and then we are so vivid in the front. And another picture here, a much closer picture, and a little diagram at the bottom that tells us a bit about where we are amongst this, in the solar system, and I'm going to talk us through that in a second. So here is the star at the centre of our solar system, which we call the Sun. And as you know from the previous videos, we have a collection of planets that orbit that Sun at the centre. Okay, now these first four are what we call terrestrial planets. They are the rocky planets. So you've got Mercury, Venus, Earth, and Mars. And then following that, you've got the Jovian planets, the gas and ice giants, which I haven't put on here because we are interested primarily today in this planet, the third planet from the Sun. And the distance from here, from the Sun to our planet, the Earth, you can see written here is 151.08 million kilometres from the Sun. And just incidentally, that should be a small k. So sorry about that. And you can see these little white lines show us the orbits of the planets. Now, the word orbit means to go around. So if you are orbiting something as we are orbiting the Sun, we are travelling around the Sun. And it takes us 365 and a quarter days to go all the way around. So if we were starting here, to go all the way around our path, around our orbit, and back to where we started, that's 365 and a quarter days, which you might recognise 365 days as being a year. And as you also probably know, every fourth year we have an extra day. We have what's called a leap year, and we have an extra day in February. And that is because every 4 years, our 4 quarters that we have extra each year have built up to a whole day, and we can add it on. So it takes us 365 and a quarter days to go all the way around, and that is our year. Now, the other quite nice thing about this diagram, which some others don't show, and you'll see an example of that later, is that this shows the shape of our orbit as well. So it shows that our orbit is kind of a squash circle or an oval shape, and we call that an elliptical orbit. It's not going round in a perfect circle, it's going round in an oval shape. Okay, and our year is different from the other planet's year because any year for any planet is the time it takes to go the entire distance around the Sun. So although ours is 365 and a quarter days, that does not mean that all planets take that long to go around the Sun. Some, if they're much further away, the ones out here that I haven't shown, are going to take much longer, and some of the ones that are going closer, that are much closer, are going to take much shorter, and obviously it depends on the speed at which they're travelling as well. Okay, so the only number we need to remember is our own year, 365 and a quarter days. Excellent. Okay, let's move on. So here's a picture of our planet. And I know you did this in geography. You can divide the planet up into 2 halves. Okay, you can have the northern hemisphere and the southern hemisphere. Now, hemi means half, and sphere is like a ball shape. Okay, so it means half ball basically, or half of this shape. So the top half near the North Pole, the northern hemisphere, and the bottom half near the South Pole is the southern hemisphere. To divide those 2 halves up, there is an imaginary line that goes around the centre of our planet, and we call that the equator. And you can see a picture of me standing on the equator here in a part of Africa, country in Africa called Uganda. And you can see I've got 1 foot on in the northern hemisphere and 1 foot in the southern hemisphere. And some of you may have been to either the same place or similar places where they have equator lines and done the same yourself. Now, the other thing which is really important to note is that this is not a vertical line. Now, this is what we call the axis. Again, it's an imaginary line, and our Earth kind of rotates or spins around what we call an axis. And if you've ever seen a globe, you'll know what I mean, because you can turn it round on that kind of line that goes through the middle. And most globes, if there are good ones, are not set up kind of with this and this vertical, like top to bottom. They're at a slight angle, as you can see here, and that's because the Earth is on an angle of around 23.5 degrees. Now, you may not understand degrees yet from maths, so don't worry too much, but it's a way of measuring an angle. And you might have heard, I'm sure you have heard of things like a right angle being 90 degrees, etc. So we're on 23.5 degrees from the vertical. Now, I'm hoping this works. I'm going to try and show you a little animation. Oh, you can see me. That's not what I want to do. There we go. So here is our Earth spinning. And if I want to, I can add in the axis, and you can see it's at that 23.5 degree angle, and the Earth is rotating on an angle like that. So it is a little bit different from what you might imagine. And it's the reason why we get seasons and things. Get rid of that. And present this again. Why won't you do that? Go away, I don't want a drawing tool. Why won't that work? Let's try again. Sorry guys, I will do this as quickly as I can. Will that work for me? Yes, okay. Sorry about that. So, let me just check I am actually recording. Good. So, what was I saying before that happened? Oh yes, I was saying that it's very important that we remember that we're on an angle, and our axis that we're spinning around on, as you just saw in the animation, is on an angle of 23.5 degrees. So let's talk a little bit more about orbit. So as I said, an orbit is where something is traveling around something else. So we are orbiting the sun, and here is a classic example of what I said earlier, of it not showing an elliptical orbit. So this would imply that we're going around in a perfect circle, which we are not. So not a great diagram, but it's very difficult to find one that doesn't do that, unfortunately. So just remember that actually this is more of an oval shape, but we are going around, we're orbiting the sun. But we have our very own natural satellite orbiting us. So this thing here, the moon, which I'm sure you're familiar with, is also going around something, but it's not going around the sun like we are. It's going around us. So it is traveling around the sun kind of as we're going, because if we're over here, it's kind of going around in a little circle, kind of almost like if you draw its path, it would be more kind of like a squiggly circular line that goes all the way around, but it's going around us and we are going around the sun. Okay, now we call this a natural satellite, as opposed to, I'll come back to that in a second, a artificial satellite. So a satellite is simply something that is traveling around our Earth. Some things that we've put there, this is a communications satellite, and we're going to talk about orbits and how things get into orbit at a later date. But it's worth remembering that we have our very own natural satellite as well. It's a big piece of rock that is orbiting us. Okay, let's go back to this one. So, first thing, and I would imagine, again, you've done this in primary school, is what causes the day and the night. Now you can see here is our Earth on its little 23.5 degree angle. Here is our axis. And there's the equator, that line, that imaginary line around the middle of the planet. So if you think about it, if this is spinning around as we just saw on that animation, then sometimes this bit is going to be facing where the sun is, and then as it spins around, it's going to be facing away from the sun. And that is simply what day and night is. It takes 24 hours for us to complete an entire spin. And so you can, if you think about it, within 24 hours, you're going to get some day and some night. And it depends kind of where you are on the planet as to whether you're experiencing day or night at any one time. But it's just to do with how the sun's rays are reaching us. So at the moment it's daytime. Hopefully you're watching this in the daytime. And on the other side of the planet, directly below us, then it will be nighttime because they are facing away from the sun's rays. And here's our moon, and remember it's going around as well. Okay. Now, just worth noting at this point, the difference between what we call luminous or reflective. Now, luminous is a word that means to emit light, okay? So something like a light bulb would be luminous. It is emitting light. And here's a picture, again taken by the Hubble Space Telescope, of some stars, and they are emitting light. They're actually giving light off. So we call them luminous. Now, some things that we can see in the night sky, such as the moon, or if you've got Google Sky Maps or something, you may well know that some of the things that look like stars are actually planets. They are non-luminous. They're not emitting their own light. The reason we can see them is because they are reflecting the sun's light. So the moon is not a luminous object. It is reflecting the sun's light, and that is the reason that we can see it. It doesn't glow. It's just reflecting light at us. Same with the stars in the sky the planets in the sky that look like stars. If you just look up at the sky, you wouldn't know they're any different, but you might be looking at a planet, and they again are not emitting light. They are non-luminous. They are simply reflecting the sun's light. However, the stars themselves are emitting light like our sun is, and they are luminous bodies. And when I use the word bodies, I don't mean like our human bodies. I'm talking about a kind of body in space. So you can sometimes call planets a type of body, a celestial body, and it just means kind of a thing of mass in space. So the stars are luminous bodies, and the moon is a reflective body in space. So different use of the word to what you're used to. Okay, let's finally touch on seasons. And this is where the tilt of the Earth becomes a really kind of key part. So here is our orbit, and I like this one because it shows that it's elliptical again. It's kind of a squashed ovally shape, and you can see that the angle remains the same. So over here we are tipped, because we're in the northern hemisphere, away from the sun, but at the other side we are tipped towards the sun, and that is what causes either the summer or the winter. So in December 21st, here is the southern hemisphere tipping towards the sun. And what that means is the southern hemisphere is in summertime. We are tilted and tipped away from the sun, so we are in wintertime. And that is why places like Australia, on the other side of the planet from us, have their winter in December. Their summer in December. Whereas the other side, where we are tipping towards the sun and Australia is tipping away from the sun, this is our summer and Australia's winter. And then you can see the other two seasons, spring and autumn, we are kind of side on. We're not tipped towards or away, we're kind of tipped to the side, but we're side on to the sun. Okay, so it's the tilt of the Earth which causes the seasons. If we didn't have the tilt and we were just kind of on this line here, then we would be pretty much the same all the way around, wouldn't we? We'd be spinning around, but we'd getting the same amount of sunlight as we move around. and we wouldn't get winter and summer. But because of this tilt, that's why we get winter and summer. And the side tilt for spring and autumn. Okay, so the only thing you really need to worry about, and the questions usually ask about winter and summer, is are we tipped towards or away from the sun during those times? So in the summer, we are tipped towards the sun, and in the winter, we are tipped away from the sun, which is, of course, why we get different amounts of sunlight, different amounts of different types of weather, that kind of thing. I'm going to go into it a little bit more about why the sun appears to travel across the sky and things like that, sunrise and sunset, but I'm not going to do that right now because I think we've done quite a lot of information there. Sorry, it was a slightly shoddier video than I was anticipating because of that bit in the middle. Hopefully you have picked up the answers to the questions I'd like you to have a go at. Oh, have I just missed an extra bit? What's on here? Oh yeah, that was just another example of the same thing, really. So here we are in summer. We're in summer. The southern hemisphere is in winter, so this is southern winter. And fewer daylight hours, less direct light, so less heat. And here is our winter and the southern summer. More daylight hours, more direct light, and more heat. Okay, and there's that angle 23.5. Again, and of course, if we didn't have that, then we wouldn't have the seasons in the same way. A bit like on the equator. The equator, because it's in the middle, the tilt of the Earth doesn't have a huge effect, so they tend to have very similar days on a daily basis. They don't really have a change in the amount of light. They don't really have a change in their weather. Whereas, depending on how far north or how far south you are into the hemispheres, then the more kind of variation you're going to get. Really quite an interesting thing if you want to read more about it. If you have a quick Google, there are plenty of places that you can read about how the seasons are kind of affected in terms of climate and things like that. Really interesting about how much water is around and how that affects the weather and the temperature. Australia, obviously, huge landmass, so very, very hot. Yeah, really worth having a look at if you're interested in kind of physical geography. Right, let's leave that there. Have a lovely rest of your day. Bye-bye.